be able to identify what makes a proportion problem, what makes a mean problem. All the ones here are mean problems, but make sure you're thinking through why is this different than the ones in the previous video. So as we talked about in the last video, we already know the framework of how to work these hypothesis tests, so we're straight into the examples. A sample of 25 IQ scores gives a mean of 103 and a standard deviation of 15. This time we're given a significance level. We don't have to assume 0.05 to test the claim that the true mean IQ is 100. Recall that IQ scores are distributed normally. Notice this is a problem you should be able to work without a calculator. All the math is going to work out nice and simple for us. So we start off with our claim. We're going to use that to get our null and alternative hypothesis, and we're going to discard that claim. The claim is that mu equals 100. The claim is that the true mean IQ is 100. So notice I shouldn't have had to say true. I should have said the claim that the mean is 100, because we know that we're always interested in claims or hypotheses about parameters, but that word true just kind of solidifies it. And you got the word mean, so you know it's a means problem, right? And so the claim would be that mu equals 100. Notice that we have a sample mean of 103. Make sure we differentiate those. Like last video, we talked about the difference between p and p hat. Make sure you can identify those in the problem. In this case, make sure you can identify the difference between mu and x bar, right? The hypothesized mu is 100. That'd be mu naught. But x bar is 103. It's the mean that came from the sample, right? So make sure you can identify those values. If we have is or is not claims, we know that the null is equal and the alternative is not equal with regards to the mathematical operator in the middle there. Check our assumptions. Nothing to see here with regards to our sampling methodology. Nothing that jumps out with regards to how we got a sample, because there's really not a lot of information about how we got the sample. And then our mathematical assumptions, remember for our proportion questions, we had to check all three. Is x binomial? What's n times p naught? What's n times q naught? Are those large enough? With regards to a mean problem, we have to go back to our gated approach. We have to say either x is normally distributed, so x bar is normally distributed, good to go, we move forward. Or if that's not the case, then we would try to see if central limit theorem holds. We would say, do we have a big enough sample to overcome any skewness in the distribution to get us to x bar being approximately normal? In this case, the problem tells you IQ scores are normally distributed. That would be x. So because my initial distribution is normally distributed, that means that x bar is normally distributed. And I can justify that just by that sentence right there. Because x is distributed normally, x bar is distributed normally, and then I'm good to go. Again, at number 2, we need to get to p hat or x bar is normally distributed, right? And if you can't, then you say, I'm going to have a little bit of concern with whatever results I have because I didn't get to that normality that I needed. We're going to next summarize into a test statistic. Now, again, this is where we would say that if we had sigma, the population standard deviation, then we could call this a z-score. However, in this problem, as with many others, we will not have the population standard deviation. This was the whole need for the t-distribution. We said if we don't have sigma, but instead we have to use s, we have to call it a t-statistic and use our t-distribution. And just as a confirmation of why that's true, if you read the first sentence of the example, it says a sample of blah, 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 blah gave a standard deviation of 15. So we're still talking about the sample, thus that standard deviation of 15 is a sample standard deviation. That is S, not sigma, because we're using S. That means our test statistic is a T. Because our sample size is 25, that's going to mean 24 degrees of freedom. So I'm going to subscript my T with 24 just to kind of remind myself how many degrees of freedom I have. Which T are we talking about? We don't subscript a Z because it's not which Z are we talking about. There's only one Z, right? The Z distribution is a normal distribution with a mean of 0 and a standard deviation of 1. There's only one of them, but there's lots of T's. So which one am I talking about? I'm talking about the one with 24 degrees of freedom, because my degrees of freedom in this problem are going to be equal to n minus 1, and then it's just plug and chug. And as you can see, this is one that you probably wouldn't need a calculator on because math works pretty simple here. The numerator would be 3, the denominator would be 15 divided by 5, also 3, and anything divided by itself is 1. And so now that we've got our test statistic, We can go ahead and set up our rejection region, find our p-value. Again, as before, we're going to work it both ways, even though you wouldn't necessarily have to come homework or exam time. You just either pick your favorite or do the one that was told. And we have a two-tailed test. Again, how do I know that? I know that from the alternative hypothesis being not equal to. And so I draw a rejection region with two tails. This problem, a little bit different than the ones we had in the last video though, because we're given a significance level, and specifically we're given one that's not 0.05. And so because our significance level is 0.1, when we cut 0.1 in half, we get 0.05 in each tail. So that's what you should write. Right here, this would be 0.05, this would be 0.05. Except now when you find these critical values, we don't go to our z-table. Why is that? Because this is a t-test. We have a t-test statistic, and so we need to find a t-critical value. So I'm going to use my t-table to find a critical value rather than the z-table. So we can't call this plus or minus 1.645 like we would if it was a z. Instead, the critical values are plus or minus 1.711. And so you'd label this 1.711 right here. You'd label this negative 1.711, and a test statistic of 1 is somewhere right in this range. Again, it doesn't really have to be to scale. The key is that you know it's not in the shaded region, not in the rejection region, meaning we're going to fail to reject the null. Let's confirm that by finding the p-value. The p-value, you can only find the exact p-value, as we talked about previously, using Excel. If you want to use your table, you can bound the p-value between two numbers, or if it runs off the table, you can say it's greater than the biggest one, or if it runs off the table the other way, you say it's less than the smallest one. But you can only bound the p-value with the table, but using Excel, you can find the exact p-value. So the MyOpenMath work will require you to find an exact p-value, so make sure you are able to do that using Excel. Write out that probability statement. Again, that's an important piece right there, just like we did last time. It's a two-tailed test, so we're going to multiply by 2. I know which direction to go because I have a positive test statistic. I'm going to subscript that t with 24 just like I did before. And using Excel, we can find that value to be 0.327. And that p-value is larger than our alpha of 0.01, so that would also lead us to failing to reject, just like we got when we worked this using the rejection region. So we're going to write that out here because our test statistic does not fall in the rejection region. Our p-value is greater than alpha. We fail to reject the null. This part works just like the problems in the previous section. So once you've done a couple of these, you kind of should have a pretty good feel for how hypothesis testing in general works. The only difference is going to be, are you using a z-table or a t-table, and exactly how do you standardize, exactly what your assumptions are, right? But other than that, the framework of hypothesis test, as we covered from those first 2 videos of this chapter, works the same way. Because we failed to reject the null, that means that we cannot conclude the alternative, or we'd say there is not sufficient evidence to conclude. Again, those are synonymous. Again, make sure you have all 5 pieces. When you write out the alternative, a population word, what metric we're using, context of the problem, the mathematical operator that came from the alternative hypothesis, and whatever number came from the alternative hypothesis. So now before we said at the 5% significance level, but now we have a significance level of 0.1, so we're going to say at the 10% significance level, there's not sufficient evidence to conclude that the true mean IQ is different from 100. Remember, we don't say not equal to. If we have a two-tailed test, we use different from just to avoid that double negative. So population word, true. Could have used average instead of mean, that'd have been fine. IQ, right? That's the context of the problem. There's no more context, right? It didn't say who the IQ scores were of. If it did, I would have added that in here, right? If it said IQ scores of, students at this university, or people of this age range, or people of this demographic, whatever it was, we'd have added that in, but none of that's listed. It just says sample of 25 IQ scores. And so we just say true mean IQ score is different from 100. As last video, this would be a decent time if you wanted to kind of work through this problem and see what you could do on your own. Then we'll come back and you can kind of validate your work with me if you want to take this opportunity. If you're still a little lost, that's no big deal. You can just kind of follow along. This example gets a little wordier, but we're considering having a fee if the entire dorm has an average thermostat set above 72 degrees Fahrenheit. You're concerned, so you take a sample of 35 rooms on your floor and find that the average thermostat is set 73 degrees Fahrenheit with a standard deviation of 4 degrees Fahrenheit. So as we talked about before, that how do I know which one's X bar, which one's mu? I took a sample of 35 rooms. What did I get? Those are sample statistics. So that's why X bar would be 73 and S would be 4. That's not sigma, right? Because that's the standard deviation that came from the sample. Now we have a different significance level, 1%. Test the claim that you might soon be paying more money, or in other words, test the claim that you might have a fee. What would have a fee? You would have a fee if the average thermostat is set above 72. So a little bit, a little worded differently here, but we should be able to put all those pieces together. Be careful, the last problem had a 0.1 significance level. This one was a 1% significance level. Be careful with moving decimal places on percentages. This turns out to be 0.01. 0.1 significance level would be 10%, right? So just make sure that we're careful with that. We're moving our decimal place the appropriate number of times. And so we have our claim that the average thermostat for all of the rooms set above 72. So the claim would be that mu, right? The average being mean, and then of all the rooms is above 72. So the claim would be mu greater than 72. So because it's a directional claim, then we know that direction is what the alternative is. So we'd have a greater than alternative, a right-tailed test, and then the null would be less than or equal to. And make sure you know why that's 72, not 73, as we talked about just a second ago. Our assumptions, our sampling methodology. Now, this is where we might have a concern, because what we did was only take a sample of rooms on the floor that we live on. If we live on the first floor, we live in the basement, we live on the top floor, you might have different things happening based off of how the sun hits the building, or people leaving windows open or not having windows, or who knows, right? And so that may affect our results, it may not, but the fact that we didn't get a good representative sample of rooms from all of the floors might be a little bit of a concern, might be something that we want to talk about here. We can't just say, oh, everything's fine with the sampling because I only got rooms on my floor that may not be representative of the entire building. Okay, so questionable sampling methodology there. Then we move on to our mathematical assumptions. Again, we start off with if X is normally distributed, X bar is normally distributed. X would be the thermostat temperature, and that may follow a normal distribution or not. It may be symmetric, it may be skewed. I don't really know, and we have nothing in the problem that tells us that. There's nothing that says the distribution of what thermostats are set to is normal or symmetric or skewed or anything. Okay, so because of that, we just have to rely on our sample size. In this case, our sample size is 35. That is bigger than 30, so we can say that the central limit theorem holds and that X bar is approximately normal. I'm going to make a note, however, that if we had a really skewed sample, that would not be enough, right? We talked about this before, that if we have a really skewed sample, right, central limit theorem says that we need much more than 30 to overcome that. If we had symmetry, even maybe mild skewness, 35 would be okay, but a lot of skewness, 35 is not going to actually be large enough. So I'm just going to make a note. If this happened to be a skewed distribution, that may not be ideal. Test statistic, as before, we're going to subscript the T with the degrees of freedom. There are 35 rooms that we sampled, so we have 34 degrees of freedom. And so, again, now we just plug the numbers in, and you should be able to get a test statistic of 1.48. This is a right-tailed test. We have a greater than alternative. That means I'm going to draw a picture and shade only the right side. I have a significance level of 0.01 because it's 1%. So I'm going to put 0.01 right here in this tail. That's going to lead me to a critical value of 2.441. And so then when I have my test statistic, it's going to fall somewhere over here as 1.48. It doesn't have to be to scale, just the idea is it's not in that shaded region. That means we're going to fail to reject. When we find our p-value, we should get the same thing. We have a right-tailed test, so we have a greater than probability statement. And Excel should give you 0.074, which is a relatively small p-value, but it's still greater than my significance level of 0.01. So I summarize that. We did not fall in the rejection region. The p-value is larger than alpha, so we failed to reject the null. And because we have failed to reject the null, that means that we cannot conclude the alternative. And so at the 1% significance level, there is not sufficient evidence to conclude that the true mean dorm thermostat is set above 72. Population word true. What metric did we use? It was a mean. What's the context of the problem? Dorm thermostat. So right-tailed test, so above, greater than, whichever word you want to use, 72 degrees. But I want to note that because I had issues with my assumptions, what does that mean? We didn't talk about this previously, but we can talk about this with all of the problems that we work, right? If you remember a couple of videos ago, we talked about type 1 and type 2 error. Type 1 error is we reject the null, but that was the wrong decision. Type 2 error is we fail to reject the null, and that was the wrong decision. Once we've made a decision, it is not possible for you to make both types of errors. It's only possible for you to make one of the types of errors. Make sure you catch that. A type 1 error is rejecting, but that was wrong. So when you reject, you got two options. When you decide to reject the null, you got two options. You're either right or wrong, right? You cannot make a type 2 error because a type 2 error only occurs when you fail to reject and that was wrong. Well, if you rejected, you can't make that error. You can't fail to reject. You didn't decide to do that, right? And then conversely, when you fail to reject, you have two options. You're either right or you're wrong. You can't make a type 1 error because a type 1 error is rejecting and that's wrong. But if you fail to reject, you can't make that kind of error. So we can always think about what type of error we could have made based on our decision. And specifically, because we have some questionable assumptions on this problem, we can say we failed to reject, which means it's possible that we made a type 2 error. And specifically, because we have bad assumptions, it's probably actually more likely than we would have thought to make a type 2 error. And so I'm going to close off this problem with a note about that.